Okay, hello students. This is a video for our beginning the introduction of the first law of thermodynamics. I'm going to introduce it today, tell you what it is in terms of words in the equation, and we're going to take a look at just one part of the equation, which is the work done on or by a gas in more detail. So let's quickly review a little bit about what the first law of thermodynamics actually says. What it really is just a restatement of the first law of, or the law of conservation of energy. It says energy can never be created or destroyed. There are, however, two ways that you can change a system's energy. You can do work on the system, or have the system do work on its environment, or you can transfer heat, which remember is just collective kinetic energy, into or out of the system. So let's take a look at an example of when we did our energy unit where that might make sense. If we consider the car, the system, and the environment, the external forces, the man pushing on it, maybe the environment there for E, we can see then that the car's energy, its kinetic energy, can be changed provided that the man does work on it. The environment does work by exerting a force some distance d. So we can change then the car's kinetic energy. We could also kind of go backwards if we can think about the system as the hammer here and the environment is the nail. The system can use some of its kinetic energy, right? It's swinging, it's going really fast, and then all of a sudden it stops. Well, where did that kinetic energy go? It was transferred out of the system by doing work on the nail, driving that downwards. So work is one way to change a system's total energy content. Heat is the other way, and that's what we've been studying more recently in thermodynamics. Heat is a transfer of energy, so it's not an energy itself, but a transfer of energy. And remember what it is, it's collective kinetic energy on a very small scale. So if we think of our coffee here as the system and the surrounding air as the environment, well, what's happening? Those particles, the coffee is hot because the coffee particles are moving really fast. They have a lot of kinetic energy. They hit the walls and they transfer some of their energy outside of the system. It leaves and makes the air or the environment go faster. So this is then a change of energy by transfer of heat into or out of the system. So keep in mind, having known that we've already studied the second law of thermodynamics actually first, that not all energy can be used to do work. The second law of thermodynamics is really the realist of the two. It says that you cannot use all of the energy available to do useful work. The first law of thermodynamics is kind of the idealist. It says, yeah, energy is conserved. You can never create it or destroy it. We can transfer it in or out as work or heat. So as profound as the first law is, right, the law of conservation of energy, the math that describes it is really pretty simple. It's arithmetic. We've got three terms, and it says this. It says that delta U, which is internal energy, change in internal energy, is heat, which is Q, minus W, which is work. So another way to say this in words was, how do you change something's internal energy? There's two ways. We could add or subtract heat, or we could have work done on the system or have the system do work. Those are the only two ways according to the law of conservation of energy. So let's just write these things down. Delta U is a change, right, of internal energy. And internal energy is basically all kinetic and potential energy in a gas. Right, and the units, it's an energy, so the units would be joules. Q is one of the first times we've seen it. Q is heat, and that's a transfer of energy into or out of a system. So if we heat something up conventionally, it would be a positive term. If we let something cool down, the system cools, it would be a negative term. But it's also measured in joules. And so is work. That's what W is, work. Work is what I want to take a little bit more of an in-depth look at today before we move much further with this profound but simple idea of the first law. So if we put thermodynamics in context with history, really what it started studying was to explain and try to make better steam engines for the Industrial Revolution. We think about a real simple setup here that we've seen in classes. If we take a balloon and seal off a flask, we have a system, right, which would be this, and we have it surrounded by its environment, which could be the flame and the surrounding air. It's not easy for us to look at a balloon and figure out, well, how much work is being done on the balloon and the flask, or how much work is the balloon and the flask doing on the environment. It's moving in all directions. The work, the force, and the distance is caused by billions of atoms hitting a surface and moving them some distance. Very difficult to do. So that's the first thing we want to take a look at today. So for a gas, it turns out that we can describe its work pretty simply in terms of its pressure. So pressure is a concept all by itself that needs a little explaining. It's definitely something used every day, but it does have a definition. Pressure is simply a force divided by an area. So this kind of silly picture here shows us the idea. The force that we're dealing with would be the weight of the woman. So the force in this case would be weight, which we know is mg. And that's the same in each one of these. What's different about it is the way that weight or that force is distributed. Here it's distributed over a pretty large area. Here it's distributed over a very small area. So even though the force is the same, this would have a much lower pressure. This would be a much higher pressure. And you can see how the artist has sort of made an indentation here in the ground. That's what we're looking at. The units for pressure, in the old English system, they'd be psi, pounds per square inch. In physics, in the new international system, we use force, which is a Newton, and we divide it by an area, which is a square meter. So 1 Newton per 1 square meter is something new to us. It is 1 Pascal. Pascal is the unit of pressure that we use in physics, and it's abbreviated capital P-A. 1 Pascal is not a lot of pressure. If we were to think about the definition, 1 Newton, well, what has a weight of 1 Newton? An apple, an average-sized apple, about 100 grams, has a weight of 1 Newton. If I were to distribute that weight over an entire square meter, so 1 meter over 1 meter, that is not a lot of pressure at all. So it's very common we'll be dealing with pressures in the hundreds of thousands, if not millions of pascals. Our atmospheric pressure is about 15 psi, a little under that. That translates to a Pascal pressure of almost over 100,000 pascals. So let's go back to this slide and recall a little bit from last unit that work, in the simplest sense, was done by a force if it's allowed to push or exert itself over a certain distance. So W equals Fd. What we've just learned then was that pressure is force divided by area. And therefore, I could also talk about the force in terms of pressure, which would be pressure times area. So let's combine these two. Here's an F, and here's an expression for F. So what if I do this? Work is force times distance. What that means is that's pressure times area times D. Now, what does that mean? Well, the pressure is the force that's exerted on an area. So let's look at this piston. Here is some area A. And we have a push from a gas, billions of gas particles pushing against that area, and it's causing the piston to move some distance. The graphic shows x, but we could just replace that with distance. So really what we're seeing is if we're allowed to have the gas or something push this piston this distance, we have a change in volume in this case. And in fact, that's what area in meters squared times the distance, meter, would yield, a cubic meter. So we can write then the work done on or by a gas as the pressure times the change in volume, delta V, capital V. Don't confuse that with velocity. So pressure, if I expand it, final volume minus initial volume. So using that definition for work done on or by a gas, work is pressure times a change in volume. If we look at this system and think of these green particles as gas molecules, and they exert a force on the cylinder in this direction, it's going to cause, perhaps you can think of this cylinder to move or increase the volume of the gas itself. So if the volume, delta V, is greater than 0, what does that mean? It means we're talking about expansion of the system. Sometimes we say the expansion of the gas or system. Then the work by the gas is a positive quantity. But gases can also be compressed. So we might imagine, a force from external, a force from the environment, pushing inward on the gas. So the force is, well, the pressure is inward, and it causes that cylinder to move in this direction. So it would be decreasing its volume in that case. In that case, delta V would be less than 0, and that would represent compression of the gas or system. So in terms of our vocabulary, the way we use the language, if we see expansion, we say that there is work done by the gas on the environment. If we see compression, we usually say that there is work done by the environment on the gas or on the system. So that's the interpretation of what a positive or a negative value for work would mean. We'll look at the consequences of positive or negative work on the energy of a system in our next unit.